Hi, this is BYU Capstone Team 17, Project Dirigible. Our project is FPGA high bandwidth memory interfacing and monitoring. Now, before I get into it, I just want to point out we have our GitHub repository linked in the description, so if you want to check out as I'm going through this, feel free to do so. It's a helpful link for all our project documentation, code, and how we approach the project. I want to give a huge thank you to Google and Tim Ansel. They really helped fund this project. Also, Florent Kimarak also gave us a lot of support as we went along this. And at Micro Enjoy Digital, they had a lot of interest and support. None of this would have been possible without them. So thank you for helping sponsor our project. Now this is us. I'm Hayden. Our other team members are Zephram, Tyler, Grant, Pablo, and our coach on the right, Eric. First, I want to talk about the motivations for this high bandwidth memory project. So number one is expand the Xilinx Alveo U280 board LiteTech support. And one of the goals for this is to really provide bandwidth measurements of the Alveo U280 boards. This means checking the throughput of the HBM under varied tests. Also, we want to expand the open source IP for HBM so other people can go in and build upon our IP. This really helps support the open source community. A little background on the project. I'll talk a little bit about high bandwidth memory. Basically, this is just DRAM, except it's stacked on top of each other, which improves some principles of locality since you don't have to go far to access the data. One of the unique things about HBM is this wide data bus. It is 1024 bits. So this gives a lot of opportunity for a very large throughput. We can see a little cross section just to give you an idea of the DRAM. We can see these TSV microbumps. So basically, these are just balls of solder which they stack the DRAM dies and connect them. And we can see these little silicon vias, which are these vertical green rectangles, which allows access between these dies. Here is the Xilinx Alveo U280 board. The whole point of this is for high performance acceleration and for computational intensive applications. Included on the board is a total of 8 gigabytes of high bandwidth memory too. And currently we are using the USB for developments. There is also options for PCIe, but we did not go into that on this project. Here's a little block diagram of the interface with the HBM. So what's important is the AXI bus on the very left-hand side. So we communicate using AXI 3 protocol to the HBM controller, which then can go to the HBM dies themselves. Now the HBM is split up into pseudo channels and memory channels, and each of the HBM controllers is assigned to 2 of these pseudo channels, and those are all controlled in the memory channel. And really important is that we're using open source documentation. What kind of makes this whole project work is something called MyGen. Essentially, this is an open source hardware description language. It's developed by the MLabs team and Florent. It allows designers to describe digital circuits and SoCs using a high-level Python syntax. What this means is it's more concise and easier to read than traditional HDL such as Verilog or VHDL. One of the key features of MyGen is it allows the automatic generation of hardware structures from these high-level descriptions. This is important because it means designers can specify the functionality of a circuit using their Python code. And the MyGen in turn will generate the Verilog or VHDL code automatically. This is also important because this reduces the time and effort needed to create and modify a designer's digital systems. There's also a couple other features like partial reconfiguration, which means you don't need to reconfigure the entire system if you change one little part of it. It's a powerful and flexible tool which simplifies the design process. Great tool for this application. Now, what is LiteTech? So this is another thing built on top of MyGen. It's an open source hardware design platform that allows developers to make their digital circuits with this collection of intellectual property. It was developed by Florent and the MLabs team as part of MyGen and the MySoC projects, and it's now maintained by a variety of contributors. It provides a library of pre-built IP cores, and these can be used to implement many functions such as the memory controllers we saw in the previous slide, Ethernet interfaces, UARTs, so much more. And these can be customized and combined to create an SoC that can meet the specific requirements of your project. Also included in LiteX are tools for generating bit streams for FPGAs and simulating designs using a hardware simulator. What this means is it makes it easy to test and debug designs before actually implementing them into hardware. So overall, it's a powerful, flexible platform for designing these SoCs, and it's very widely used now. Here is the original Alveo U280 LiteX project for the HBM. So originally we were communicating over UART over a VEX RISC-V CPU. Now this CPU can communicate to the controller through only 4 AXI controllers. What this means is there are 28 other controllers that are being unused, and these are connected to the HBM.
Now we will present our project. As a reminder, here is a link to our GitHub repository. The requirements for our project are using Python 3.6 or above and Vivado 2021.1 or above. These are the commands to install MyGen and LiteX. On the left, you can find the commands to add the remote repository for LiteX, and on the right, you can find the commands to add the remote repository for LiteX boards. The goals for our project include the following. Add new BIOS commands to control each of the bandwidth generators that are connected to the HBM boards. Each bandwidth generator is able to perform continuous transactions for either reading or writing, and you can even add a delay to them. All of the hardware and software is implemented using the LiteX and MyGen open source tools. You can measure the throughput of all 32 HBM ports over time, and you can see the results through a simple GUI. All of the hardware modules were implemented using MyGen and LiteX, and all of the BIOS software was written in C. These are all the files we generated and modified to implement our project. To debug our project, we use the integrated logic analyzer found in LiteX, and we use the Quested Sim simulator to simulate the HBM IP in Vivado. This is the current architecture of our project, which runs the Python script in the host CPU, which then interacts with the VEX RISC-V CPU via the UART. Then there's a LiteX server running in the VEX RISC-V CPU that uses the BIOS commands to set the control status registers that enable each of the bandwidth generators that interacts with the high bandwidth memory. The FPGA board interacts with the host CPU via the micro USB.
Now we will talk about the bandwidth generator. This is about the state machine and software behind our HBM tester. This is the overview of our HBM reading and writing state machine. The state machine supports continuous reading and writing for each AXI3 port in the HBM controller, not concurrent reading and writing. We used and extended the default C program in LiteX used by the RISC-V processor called the BIOS. This program contains commands for reading and writing to the main memory, and also other various commands for other functions such as resetting the SoC and using other components such as LEDs. We added 5 commands to the BIOS for reading and writing to the HBM. These commands read and write to the CSR registers, which control the state machine, which we added to our hardware. The order that these functions should be used are as follows. Use the HBM read set function and HBM write set function to control the settings for which ports should read and write. Then, run the function HBM test start to start all ports reading and writing at the same time. Whenever you want to display the data, run the function HBM bandwidth. This will pause all the running ports and their current data variables, and the current number of reads, writes, clock cycles, and speeds in megabytes will all be displayed for every port. Whenever you want to reset the settings after starting the port, run the function HBM test finish. This will stop and disable all ports from reading and writing. These functions will all be described in more detail in the following slides. Here is a description of input and output CSR registers. These ones are common. These ones are shared by all of the bandwidth generators, and you can look at these descriptions for reference after the presentation. For now, we will give a brief summary of each. These are CSR registers common to each of the 32 ports in their state machines. The port mask register is a 32-bit signal used by the HBM read set and HBM write set functions to enable whichever ports are desired for reading and writing. The start register starts all enabled ports to read or write at once and disables them all at once. The data pattern register, only used in the HBM write set command, controls what data pattern to write to the HBM. The delay force register forces all running ports to stop in a pause state. This is useful when getting data with the HBM bandwidth function. Next are individual CSR registers. Instead of these being common to each port in the state machine, each of the 32 state machines have their own register named after these. This allows us to more flexibly control the settings with the data that we send to our HBM tester. The port settings register is a 1-bit register that controls whether the specified port will be reading or writing to the HBM. The rest of the registers, total reads, total writes, and ticks, are each 32-bit counters continuously running in the state machine. These continuously count up while the port state machines are running, and they reset after reaching the number of bytes specified by the user that this port should read or write to. When obtaining the data for the speed of each port with the HBM bandwidth function, each of these counters will pause, and software will take this data and calculate the speed and throughput. Here are more individual registers used by the HBM write set and HBM read set functions, and they control more of the settings for the state machines reading and writing to the HBM. The address read-write register controls the address of which the port should write to. The burst length register controls the number of bursts that should happen in a transaction. The last burst length register controls the number of bursts that should happen last in a transaction. The burst quantity register controls the number of transactions for either the reading or writing command. In software, these are all calculated based on the number of bytes the user specifies the port should read or write to the HBM. Next is the delay counter register, delay counter max register, which defines how many clock cycles each state machine should wait after performing the number of transactions and bursts specified by the user. And lastly, the last two registers are 1-bit status registers. The delay state machine register is a register that goes high whenever the state machine has entered the pause state. So, when forcing all the ports to pause, we can check that each port has indeed paused in this state. The other register is execute done, which goes high if the port is currently disabled and in the wait state. Here's a simplified finite state machine for reading and writing. All 32 state machines, one for each port, start in the wait state. This represents all 32 state machines, and they all start in the wait state, and first the port settings are set to read or write a certain amount of bytes continuously. Then a universal register called start starts all these enabled ports at once to read or write this number of bytes. Data is obtained by forcing all the start states into the pause state and reading CSR registers, keeping track of the total number of transactions and clock cycles. When the user specifies that the state machines should stop, all ports go back to the wait state. Here is an example of using the HBM write set command, along with a state machine and a list of all the CSR registers. The CSR register port settings is set to 1, the write setting, and the arguments are as follows. The bytes argument specifies the number of bytes to write. This is required. In software, this helps with the calculation of the number of transactions and the number of bursts within each transaction. In this case, the ports will each write to 768 bytes in 32-byte bursts. One transaction will be a burst length of 16. Register burst len is set to 16. The last transaction will be a burst of 8, so the last burst len register is set to 8. There will be 2 transactions, so burst quantity is set to 2. And in all, we will have 24 32-byte writes with the HBM. The rest of the arguments are optional, as there are default values for each. The port mask is a 32-bit signal where 1 enables a port to run. For example, if the least significant bit is 1, port 1 will be enabled to write. The default value is all 1s. This sets the port mask register to the appropriate value. The delay val is a 32-bit signal specifying how many clock cycles to wait in the pause state after reading or writing a specified number of bytes. The default is 0. If the delay is set to 32, The state machine will wait in the pause state for 32 clock cycles immediately after the read or write. If the delay is set to 0, the state machine will not enter the pause state and immediately perform another write. Address. The next argument is the starting address of the first enabled port. The address is 33 bits wide. The last 5 bits are unused, so to get around this, we created a CSR register that is 28 bits wide and shifted to the left by 5 in the state machine. So the default value is 0, and the address offset is the next argument, is the value that controls the starting address for every other enabled port. The default value is an 8 followed by 5 zeros. And in our state machine, this would look like a 1 followed by 7 zeros. So both the address and address offset arguments contribute to the value of the register address read-write for each of the 32 state machines. For example, if the first 16 ports are enabled and the starting address was 0 and the address offset was 1, then port 1 would start writing at address 0, port 2 would start writing at address 1, port 3 at address 2, port 4 at address 3, and so forth, until the last enabled port 16 would be writing at address F. The data pattern is a 32-bit signal controlling the pattern of data written. This is the next argument. It is replicated 8 times and concatenated to create a 32-byte data value to be written. The default value is in hex A5, 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 A5. This is the HBM read set command. This initializes the settings for ports to perform a continuous read. All of the arguments are the same as in HBM write set, except that there is no data pattern. The CSR register port settings is set to 0, which is the read setting. Each port will read 1024 bytes of data. 2 transactions will be a burst length of 16, thus burst len is set to 16. The last transaction will be a burst of 16, and since it isn't different than burst len, it is not set. There will be 2 transactions, so burst quantity is set to 2, and in all we will have 32 byte writes with the HBM. In this case, because port mask is set to FFFF0000 in hex, only ports 17 through 32 will run, and they will all be set to read. The delay is set to 0, so the state machine will not enter the pause state and immediately perform another read. The address is set to 0, and the offset is set to 8 followed by 5 zeros. So the first enabled port is port 17, so this port will start reading to address 0. Thus, port 32 will write to address 0 plus 8 followed by 5 zeros times 15. This is the HBM bandwidth command. When running this command, all the data is displayed for every port. The register delay force is set high, and all running ports will go to the pause state after reading or writing the number of bytes. Once all running ports are in the delay state, checked with the status register, the total number of reads, writes, and clock cycles are read. The speed is calculated in software. After all the data has been obtained, the delay force register is set low, and the ports start to continuously read or write again. Lastly, this is the HBM test finish command. This sets the CSR register start low, and all of the port state machines will go to the wait state. This command finishes once all have made it to the state. Port mask, which enables the ports, is reset to 0.
Hi, this is Zephram Tripp from Team DRGBL, working under the BYU Capstone program on the High Bandwidth Memory Interfacing and Monitoring project. As part of our project, we developed a simple GUI for running our test that we created for the high bandwidth memory on the Alveo U280 board. This uses the LiteX terminal and the LiteX server to communicate with the board over UART, and that allows us to send commands using various CSRs on the board, one character at a time, and that allows us to run the various tests for the high bandwidth memory. And I'm going to give a simple example of how the GUI works. So as you can see, I'm already in the directory where we hold our LiteX files. From this directory, we first have to source our Python in virtual environment. This will allow us to access all of the various different dependencies that we need to have our project work. The next thing I need to do is source the Xilinx Vivado tools. You don't always need the Vivado tools for LaTeX, but we've chosen to use those tools in particular for our project. So those are the ones I'll be sourcing this time. We use version 2022.2 in particular. So now that we've sourced those tools, we just need to start up the LaTeX server. And we do that by running this command. Once we run the command, you can see that the server is working on a particular port. In your particular case, you'll probably have to change which port it's acting on depending on your system and implementation. Then, to activate the GUI, we just run this command to run the script that activates the GUI. So here's the GUI, and as you can see, it has a few different parts and functions. It has a field for the number of bytes to read and write in a transaction. It has the ports that you want to assign to read and write encoded as a binary stream. It has the delay time between transactions and cycles. It has a starting address for the first read and write of a transaction, the address offset between subsequent reads and writes, and the data byte pattern for writes. All of these are options that we can set to do various tests on the high bandwidth memory. Then we can either set the assigned ports to read or the assigned ports to write, and we can start the transactions on all assigned ports. We can get the data from them by pausing the transactions and sampling the overall throughput, and then when we're done with the test, we can stop all the ports using the Finish button. If we want to have some automatic collection, the Start Collecting button collects the results every 6 seconds for 1 minute. And the Resize button allows us to resize the graph to fit whatever screen size we have available at the time. So just as a short example, let's say we want to write FFFF bytes to the bottom 16 ports of our machine, and we don't care about any of the other things. So we can just set them all to write, and then we could start it, and then we can get the data. Now it'll take a couple seconds to get the data, but as you can see, we now have 0 data points, so it doesn't create a very interesting graph. But if we get data again, and wait a couple seconds, then we can see it's about the same across the 2 samples. And so it creates this straight line on the graph. And then if we finish this test and switch it to reading instead, and then we start it up again, and then we get the data again, then we can see that the reads have a much different throughput than the writes. And so if you collect a bunch of times, you can see those things get graphed over time. And various other settings will cause you to get different results as well. And that's all. That's all the GUI has, except for, I guess, the last thing is the Help button. If you need additional help, clicking on the Help button will link you to our wiki, which has information here on the right-hand sidebar for the GUI tutorial. And that will help you with any other issues you might have with the GUI. Thanks for watching. Hope you have a great day.
Now we would like to go over our results and limitations of our project. For the throughput, for the Alveo U280 board, you can get 460.8 gigabytes a second. Now the way that math works out is there's the 256 bits per AXI port times 2 ports per memory controller times 8 channels at a frequency of 450 megahertz. If you do that math out, you'll get roughly 1,843,200 megabits per second per stack. So you can change that to megabytes, which would then be 230,000 megabytes per stack, and then you multiply that out and you get, or multiply that by 2, and then you get the 460.8 gigabytes per second. Now, our current implementation gets roughly 70.08 gigabytes per second, which roughly translates to 84 gigabytes a second. So we are only getting 18% of the theoretical max. Our clock rate for our AXI is currently only at 150 megahertz a second. So if we use
the math they already did to calculate the maximum throughput at the correct value, then you can find that our theoretical max is actually only 153.6 gigabytes a second, which is 54%, which is approximately what we would expect because we can only do a write or a read. But if we could do both at the same time, then that would double our throughput and get us close to what we could possibly do. Now, some things that are impeding our throughput are the AXI 3 ports are only running at 150 megahertz versus the 450, which is recommended from the Xilinx documentation. And the read and writes can't be done simultaneously, and we're not queuing read and write transactions, so there is going to be extra space in between when we are transferring data because of how AXI works. All of this information can be found in the Xilinx HBM documentation, which you can find here through this link, and you just have to go under Designing with the Core, HBM Performance Concepts, then under HBM Topology you can find where we found out how the layout of the HBM is, and then you can also find their calculations for the raw throughput and the nuances there with that, and then also the AXI considerations. And one of those AXI considerations is that with our specific board, even though the theoretical maximum is 460.8 gigabytes a second, the actual maximum that we could achieve is 9% less than that. The actual theoretical maximum is roughly 420 gigabytes a second. Now, as for future work that needs to be done for our project, specifically with the bandwidth generator, we wanted to implement a better AXI 3 protocol so that we can do parallel reads and writes, which would look something like this, where we have the two different state machines each functioning so that they can do reads and writes, and then also queuing up reads and writes. Now, the HBM can queue up to 32 write transactions and 64 read transactions at a time. And by doing that, we would be able to do even more reads and writes. And then also with the bandwidth generator, adding stuff like random addressing, creating scripts that would then do a suite of tests that would do random addressing, switching between reads and writes, doing continuous reads and writes on the same port, and then also being able to add other functionality or grab different data, because we are currently only grabbing the number of clock cycles, the number of bytes that we're sending through by counting the number of bursts of data that we pass through and calculating our throughput that way. But there are other things that we could do to calculate that. And like the AXI implementation for our project, increasing the clock speed up to the 450 megahertz. This is half of the HBM's clock speed, which is how it transfers the 256 bits, and that is what is recommended in the Xilinx documentation. Now, some other things that could be worked on are also changing the project so that it could work over the PCIe port instead of through the USB port, because that does have its drawbacks and limitations for how fast you can talk to the code running on the RISC-V processor, and also adding other BIOS commands for further control over the bandwidth generator. Maybe there's a specific functionality you want to change, like the exact number of bursts in any given transaction, forcing it to always be one thing, instead of trying to get the maximum speed or something like that. Now, in conclusion, I wanted to point you all back to our GitHub repository, so you may be able to look at what we've done, what we're doing. We have a wiki built on this repository that has all this information, and we want to thank Dr. Worthland, Dr. Goders, and Eric Quist, our team coach, with everything that they've done to help us through this project be able to complete it. And as always, thank you, and shout out to Google for them being able to sponsor this project, provide an opportunity for all of us to learn about the amazing possibilities that exist through open source FPGA design, and being able to participate in something that will be able to provide a foundation for others going forward in using these new open source tools. Thank you very much.